Welcome! This is the video for introducing the lab Electromagnetic Waves and Coaxial Cables for Physics 121 at Bryn Mawr College. At this point you may be asking, what is a coaxial cable? Well, a coaxial cable is designed to transmit high-frequency signals. It is made up of a round copper wire and 3 layers of insulation: plastic insulation, a wire mesh, and an outer sheath. Even though it looks like a single wire, a coaxial cable is actually 2 wires, so that when you connect it, you are creating a complete circuit. The heavy insulation of the coaxial cable protects the electronic signal traveling through it from outside magnetic and electronic fields, and means that there is only a very small amount of leakage. It might be easy to think that the electronic signal traveling through the coaxial cable is analogous to a light wave traveling through space. It has very little interfering with it after all. But what our signal is traveling through isn't the vacuum of space, but rather the material of the wire in the cable. And that material has a specific impedance, or resistance, depending on the dimensions and the materials used to make the cable. Resistance, or impedance, is defined according to Ohm's law as the ratio between the voltage, V, and the current, I, and is denoted with the letter R for resistance or Z for impedance. To avoid confusion, we will be using the letter Z for the remainder of this presentation. So what are voltage and current? We can think of voltage as the work needed per unit charge, or as the electronic potential difference between 2 points on a circuit. We can use the unit of volts for voltage. Current is the amount of charged stuff flowing through a circuit at any given time. We use the SI unit amperes to describe current, which is the flow of electric charge across a surface of 1 coulomb per second. So how does this help us define resistance? Since resistance is the ratio between the electronic potential difference and the charge moving through a circuit, we can describe it as the measure of an object's opposition to the flow of current. Now, let's imagine an electromagnetic wave traveling through a coaxial cable until it reaches the intersection between the cable it's in and a new cable. This new cable has a larger impedance. What happens to the wave? Since cable 2 has a higher opposition to the flow of electric current, some of the charge will be unable to continue traveling in the same direction, and will instead be reflected back into the first cable. Imagine it like light hitting a pane of glass. Some of the light is transmitted through the material, while some is reflected back at the same angle. The ratio of the amplitude of reflected current to the amplitude of the original signal is called the reflection coefficient. But what about the signal that continues traveling through to the second cable? We have a coefficient to describe that too, the transmission coefficient. This is the ratio of the transmitted amplitude to the initial amplitude of the wave in the first cable. Because each of these are the fraction of the signal that is reflected and transmitted, respectively, we know that the coefficient can be at most 1. Also, the more it is reflected, the less it is transmitted, and vice versa, so R plus T equals 1, assuming no signal is lost. Now, let's imagine that the resistance of the second cable is massive compared to the first. That is, it's extremely hard for current to travel through it. What would we expect the reflection coefficient to be? In this case, almost all of the signal traveling through the first cable would be reflected, so the reflection coefficient would be close to 1. On the other hand, since almost none of the signal is transmitted to the second cable, the transmission coefficient would be close to 0. Now what if the resistance of the 2 cables are equal? In this case, all of the electric signal traveling through the first cable is able to transmit through to the second, so T is equal to 1 and R is 0. Now that we know the characteristics of an electric signal in coaxial cables, we can measure the speed that a signal travels through a specific cable. By connecting a pulse generator and an oscilloscope, we can show the moment when a signal arrives at a machine. In this case, if we have a long cable, we can measure the difference between the first incident of a signal and the reflection at the very end of the cable, and use that to measure the time it takes for the signal to travel to the end of the cord and back. Therefore, knowing the resistance of a particular cable, we can calculate the speed of the signal it travels in. So how do we investigate the concepts we've discussed in the coaxial cables lab? Here's a brief overview of how the experiment works. The pulse generator equipment on top generates a pulse, or an electromagnetic signal, with a fixed time interval. That pulse, or wave, travels through the cables in the back of the pulse generator. The resistance in the pulse generator and the cable are matched, which means that 100% of the wave generated is transmitted into the material. We can then visualize these waves on the screen of an oscilloscope. From the oscilloscope, the pulses travel through the cable at the back end and can be reflected or otherwise transmitted into something new. By experimenting with this apparatus, we hope you will be able to visualize some of the concepts we've learned and understand more about electromagnetic waves and coaxial cables. Thanks for watching!